Hello viewers, my name is Bimbo. I'm a data analyst with over 10 years experience. I have worked on many data sets from several projects, some of which are hypertension and preventable lifestyle risk factors, reproductive health among secondary school students, hepatitis B immunization uptake among health workers, prevalence of soil transmitted helminth infection in primary school pupils, risk factors of acquisition of Helicobacter pylori infection, leading causes of childhood mortality, hospital-based study, knowledge, attitude and practice of infant young child feeding in selected local government areas in Niger State, a project of UNICEF in collaboration with Kaduna State University. Maternal, newborn and child health survey in Kebbi State, also a project of UNICEF in collaboration with Kaduna State University. Y poliovirus vaccine administration in Nigeria with a social mobilization team of the World Health Organization in Abuja and a host of others. In my journey over the years as a data analyst, I've observed that some students and researchers alike desire to analyze their data by themselves or wish to interpret the results of the analysis they run. However, they face some issues such as faulty design of data entry template which does not adequately capture the data from the field, challenge of coding open-ended questions without losing important information, handling multiple response variables, choosing appropriate statistical tools to answer the objective of the research, understanding the data types and the measurement level for the proposed statistical tool, difficulty in carrying out the process of analyzing the data, understanding the results and interpreting it correctly. In an attempt to provide solution to some of these challenges, I have decided to put up this video to explain underlying assumptions in conducting linear regression analysis. I will take you through the steps of running the procedure of performing linear regression analysis and also interpret the results. So I enjoin you to pay rapt attention, don't get distracted and watch this video to the end. I assure you that it will change your data analysis experience for the better. So come with me. You're welcome once again to this video. We'll be discussing regression analysis. Linear regression is used to predict a dependent variable from one independent variable or more than one independent variable. If you're predicting from one independent variable, then we're talking about simple linear regression. But if you are predicting from more than one independent variable, then we're talking about multiple linear regression. The mathematical model derived from regression procedure can be used to predict future values of dependent variable based on input from available independent variables. However, the dependent variable of linear regression model must be measured on a continuous scale. There are assumptions to meet in performing linear regression analysis. When we talk about multicollinearity, the independent variable must correlate with dependent variable on at least r is greater than 3, where r is the correlation coefficient, and the independent variable themselves must not correlate with one another. In your result, the tolerance should be greater than 0.1 or IVF less than 10, else there's likely to be a problem with multicollinearity. The dependent variable must be normally distributed. Then the dependent variable also assumed to have equal variance across the range of values of the independent variable. Like I said earlier, dependent variable must be measured on a continuous scale. Then you should note, the more the number of independent variables you want in your model, the larger the sample size should be. Don't have a long list of independent variables for a small sample size. There are other things to also check in performing linear regression analysis, such as identifying outliers, because regression analysis is susceptible to outliers. One of the ways in identifying outliers is the use of standardized residual. So if a case has standardized residual greater than 3, you may have to check. It could be an outlier. If more than 1% of cases have standardized residual greater than 2.58, or more than 5% of the cases have standardized residual with absolute values greater than 1.96, then you could go back to your original document, your source document, to determine if these cases are actually outliers or not. You should also look out for inferential cases. A case is said to be inferential if removing it from analysis gives a very different model. One of the methods to identify inferential cases is the use of Cook's distance. Cook's distance is a measure of the overall influence of a case on the model. When this value is greater than 1, then it is significant and may be an inferential case. So we have a simple regression model equation here as y equals alpha plus beta x, where y is a dependent variable, alpha is the intercept, also known as a constant, is the value of independent variable when dependent variable is 0. Then beta is the slope. It is the amount by which the dependent variable changes for a unit increase in the independent variable. The independent variable here is x. Now we'll be using a sample data of hypertensive patients whose systolic blood pressure and related risk factor variables were documented. The significant level is set at 5%. So continue. So we'll be taking an example to demonstrate running a simple linear regression. A researcher wishes to determine if weight significantly predicts systolic blood pressure. Of course, we set our level of significance to 5%. So we'll go back to our sample data, click on Analyze, down to Regression, then click on Linear. So our dependent variable here is systolic blood pressure, which is SBP. You click on the arrow that takes the dependent, and our independent variable is weight in kg. Click on it and take it to, click on the arrow that takes it to independent box. Alright, so you click on OK. Okay, so we have the result of our simple linear regression. Now the independent variable we used is what is highlighted here as weight in kg, and the second table shows the model summary for our correlation coefficient, which is 0.444, as we saw earlier when we ran the procedure for bivariate correlation. Alright, and R squared of 0.197. Then the third table shows the ANOVA table for the regression, and we have a p-value of 0.000, which shows that weight significantly predicts systolic blood pressure. Alright, then the result here, R squared, shows that 19.7% of variance in systolic blood pressure can be explained by weight. Okay, then this last table we have here is table of coefficients, and in the second column where we have B now is the coefficient for alpha and the coefficient for our independent variable. Alright, beta, the constant value is 79.234, which is alpha in the simple model equation we saw earlier. Then beta, the coefficient for x, the independent variable, is 1.719. So if we fit in these values for alpha and beta, we can significantly predict what systolic blood pressure will be if we have a known value for weight. Alright, so the same researcher wants to determine if weight, age, total cholesterol, and family size significantly predicts systolic blood pressure. So we'll be running a multiple linear regression now. We'll go back to our sample data. Alright, go to analyze, down to regression, still on linear, click on linear. Alright, our dependent variable is systolic blood pressure, SBP. You take it to under the dependent box, and our independent variables are age, total cholesterol, family weight in kg, and family size. Alright, okay, so you go to statistics, click on the button statistics, and check confidence intervals, check on R-squared change, descriptive, part and partial correlation, collinearity diagnostics, and case-wise diagnostics. Reduce the standard deviation here to 2 and click on continue. Alright, click the button of plots, then the standardized predicted value, you click on it and take it to the x-axis, and the standardized residual, you click on it to take it to the y-axis. Click on histogram and normal probability plot, then click on continue, then you click on save, and under residual check the standardized, and under distance you check Cooks and click on continue, then you click OK. Now we have our results. The first table shows the descriptive statistics of our variables with their mean values, the standard deviation, and the number of cases in the data set. Now the second table is table of correlation, showing the relationship between the dependent variable SBP and the independent variables. As we can see, age has 0.183 our relationship with SBP, meaning that there's a positive though weak relationship between age and systolic blood pressure. Then systolic blood pressure also has a positive weak relationship of R equals 0.209 with total cholesterol, while it has a moderate positive relationship with weight of R equals 0.444 and a strong positive relationship with family size of R equals 0.646. And if we look down in the second row of the table, the p-values for each of those variables are significant. Alright, so the table of model summary shows the correlation coefficient of 0.658, alright, which is a strong positive relationship between the dependent variable and the independent variable, and it has R squared of 43.3%, which is an improvement on the simple linear regression we performed earlier. As we can see here, we had R squared as 19.7, whereas we have R squared here as 43.3%, and you can see even the correlation coefficient in the second model is stronger. Here we have it at 0.44, but in the multiple regression it has improved and we have it at 0.658. all right, so and we can see that it is significant from the ANOVA table here with p-value of p equals 0.0001. okay, so looking at the table of coefficients, so this side of the table we'll see collinearity statistics, where we have our tolerance values all greater than 0.1 and VIF values all less than 10, which means we do not have issues with collinearity, multicollinearity among the variables. all right, then here we have the under unstandardized coefficients. We have the coefficient for the constant alpha, which is 85.349, and that for age as minus 0.155. we have for total cholesterol as 0.015, and for weight as 0.598, and the coefficient for family size is 8.301. significant results for each variable. We have only weight and family size as contributing significantly to the model. all right, we have a histogram showing that the standardized residual follow normal distribution, which means dependent variable solely blood pressure is normally distributed. all right, and okay, looking out for outliers, we can check the case-wise diagnostics table and look out for cases where we have standardized residual greater than 3, and in this case we have just one case. all right, then we can look through to see how many of the cases we have that have standardized residual greater than 2.58. so if we look at these cases and putting them together, they are no more than 1% of the sample size, then we're okay. But if it's more than 1% of the total records we have, then it might be important to have a critical look and check if those values are actually outliers or they are real values that should be there. all right, we can also check if the number of cases that have absolute value of 1.96, if they are more than 5% of the cases, then we may attribute them to cases that are statistically outliers. But actually for this particular data, the values have been checked and none of them really is an outlier from the original source. But if you are running your own data set and you have cases such as this, you might just go back to check case number 167, for instance, to be sure that the value you have for the systolic blood pressure there is what it should be from the source document. Alright, also look at the scatter plots to check if the dependent variable is assumed to have equal variance. The observations we have here are scattered around the graph, and we cannot design a particular pattern which shows that the dependent variable is assumed to have equal variance across the range of the independent variables. So in summary, we'll be choosing weight in kg and family size because they are the variables that are contributing significantly to predicting systolic blood pressure. I hope you have enjoyed this class and learned a couple of things. However, I understand that there are several other statistical tools you may require to analyze your data. In view of this, I have painstakingly put together a package of 5 courses which contains several statistical procedures, as will be displayed on the screen next. Amazingly, this course also comes with 3 months free follow-up consultation for duly registered students. So register now for a comprehensive power-packed video courses where you learn the following: basic statistics principles, data analysis and interpretation, hands-on with sample data using SPSS. On a norm, I charge 15,000 naira for each course, meaning that the 5 courses should have been 75,000 naira. However, the sales price of this pack of 5 courses is 20,000 naira only. But here is what I'm going to do for you. For the sole reason that you watch this video till the end, I'll give you this pack of 5 video courses for 5,000 naira. But this offer lasts just for 48 hours. So register now. My bank account details and contact details are displayed on the screen. After payment, you can send your proof of payment to the mobile WhatsApp number 08089138183 to gain access to your course. Thank you for watching, and bye bye.